Mr. Tarou, well, we're continuing that work and getting ready for the AP Calculus exam. And in this short video, we're going to be taking derivatives of absolute value functions. In the description, you will find a link to the full review playlist, all these questions inspired by multiple choice questions I've used in the past 4 years. And you'll also find links to any full-length lessons that I've done that apply to these concepts. Now, I have done a lesson on finding derivatives of absolute value functions, and in that lesson, I worked on rewriting these equations in terms of sort of like, well, when you take an expression and you square it and then square root it, that acts the same as an absolute value function, and we approach the problem, those problems that way. But this time we're going to look at it a little bit differently. We're going to rewrite these equations into a piecewise function, and then take the derivative of the piecewise function. A couple of years of experience of teaching calculus has learned that's a little bit easier, or maybe a lot easier, than how I did my first lesson. So we're going to walk through the first example, but because this is a review, I'm going to give you some time to practice number 8 on your own, and then just reveal the solution a little bit at a time. So the first thing you want to do when you find the derivative of these absolute value functions, if you want to go through the process of this piecewise function idea, instead of the square rooting of a squared value, is, and that's true regardless of what technique you use, you have to remember that these absolute value functions are all going to have a sharp bend at the values, generally, that make the expression inside the absolute values equal to 0. It's kind of like a critical value. So we're going to take this 2x minus 3, we're going to set it equal to 0, and of course solve. So that's going to be x is equal to 3/2, and that's the break. Okay, and this is just a simple linear function. This absolute value function is going to have a sharp bend at the x value of 3/2, or 1.5. So we're going to say then that y is equal to, well, let's see here. If we put a number in that's larger than 1.5, like 2, we're going to have 2 times 2 is equal to 4, minus 3, which is equal to 1, and the absolute value of 1 is just 1. So the absolute values don't really seem to be doing anything. It tells us how far value is away from 0 on the number line, but really numerically nothing happens. So we just go, okay, so we have 2x minus 3 plus 1, and that's going to be our function for all x's that are, well, going to be, and I kind of want my conditions to kind of go from low to high. So actually, the absolute value symbols did nothing per se when x was greater than or equal to 3/2. If you do put in 3/2, then 2 times 3/2 is equal to 3. And then 3 minus 3 is equal to 0, and the absolute value of 0 is also just 0. There's no sign change. But when you plug in an x value which is less than 3/2, and let's just pick 0 for convenience, 2 times 0 is 0. The absolute value of negative 3 is a sign change, and the actual answer, of course, is equal to 3. So we show the effects of that absolute value function, if we're rewriting this in pieces, as introducing a parentheses with a multiplication of negative 1, just like we would have done solving absolute value equations back in Algebra 1 or Algebra 2, whenever it was you were exposed to it first. So absolute value, changing the sign when x's are less than 3/2. Of course, we can distribute this negative, combine like terms, and we have y is equal to, it's now a piecewise function, negative 2x. Negative times negative is positive, and then 3 plus 1 is equal to 4. And that's when x is less than 3/2. And we have 2x minus 2 for when x is greater than or equal to 3/2. And now we just have a nice little simple linear function in 2 pieces to take the derivative of. So y prime is equal to negative 2 when x is less than 3/2, and the derivative of 2x minus 2 is just equal to 2 when x is greater than 3/2. Now do you see what I just did there? Not only as I do this, I think, man, in the previous lesson I would have wrote this as y is equal to the square root of 2x minus 3 squared plus 1 and then go through that process. And it was a lot more complicated than it is by rewriting it in terms of a piecewise function. Secondly, notice that I'm saying that the domain of the original function, because the domain of this absolute value function is all real numbers, so I'm showing that in the piecewise function. But when I get down to the derivative, I've lost the equal sign, of course, because y prime is not the derivative for this function is not equal to 2 at 3/2, of course, because again, that's a sharp bend. You can't find the derivative at a sharp bend. Take this idea and see if you can't find the derivative for this absolute value function. A little bit more complicated because it's not a linear function. And I'm also going to reveal the solution one step at a time. Every few seconds, reveal the next step in case you get stuck and you want to pause it and then finish it up. And we'll also look at what the graph of the derivative looks like as well. Coming up, that's right first, right now. Now, first of all, love my chalkboard graph paper grid there. And always get all kinds of people asking me, well, how do I draw these dots? If this is a parabola, now in my Algebra 1 class, I'm talking about graphing right now of parabolas with transformations. And we have a basic parent function shifted to the right 2 and down 4. So we'd have a parabola opening up. But of course, the absolute value, this is all inside the absolute value symbol or function. So anytime this expression comes out to be negative, of course, the absolute value is going to make it positive. And our graph will look something like that. Now, I could do maybe a t-table to get a slightly better accurate picture of how sharp the slope is there to the left and right of 0 and 4. But now comes the graphing of piecewise functions. All these things we learn, it's so cool, keeps tying us, coming back and getting used again. We have just a y-intercept of 4, negative 4, and a slope of 2. So 1, 2, 3, 4, and up 2 over 1. Now, this is only defined when x is less than 0. So even though, we'd have a line like course like this, and I'm speaking for anybody watching this that is not necessarily taking calculus, because this is a review of graphing piecewise functions. So we have a function, a line, slope 2, y-intercept negative 4, going to be true all the way up until when x is less than 0. And then between x being between 0 and 4, did you notice that in that middle part of this piecewise function I included that the negative sign? And how I know, of course, the absolute value is going to take care of those negatives and switch the sign of our answer comes in two ways. Either I can, plug in an x value of, say, 1, right? Because we had those two critical points along the x-axis where the sharp bends are for the absolute value function. So I know something's happening to the left of 0, and between 0 and 4, and to the right. And I can plug in points. Like I can say, well, let's let x be 1, and 1 minus 2 is such and such, and work out the arithmetic. Or just understand, of course, we are just talking about a parabola, and we're in calculus now. We should know what that thing looks like, knowing that that graph was falling below the x-axis there, requiring us to introduce that negative set of parentheses to change the sign like the absolute value symbol would do. So between 0 and 4 then, we have this line y equals basically negative 2x plus 4. So now our y-intercept is positive 4. But of course, we can't take a derivative at a sharp bend, so that's undefined. Slope's negative 2, so down 2 over 1, down 2 over 1. And just keep on going, making a nice solid line until we get to that x value of 4, where we have that other sharp bend. And then picking right back up, well, when x is greater than 4, we didn't have that sign change, so we're back to that 2x minus 4 line. So coming way back over here, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, pick up with that open dot, and voila, We've done a little review of dealing with piecewise functions as well as parabolas using graphing parabolas using transformations. I'm Mr. True. Bam! Let's go get that 5.